In the world of higher mathematics, progress is often the result of immense collaborative effort with incremental advances built upon decades of shared knowledge. It is a world of seasoned experts, established paradigms, and problems so difficult they can define a career. So it's not every day that you see the world overturned by a teenager working on an optional homework problem, but that's exactly what just happened. On February 10, 2025, a paper appeared on a preprint server that sent a shockwave through the advanced mathematics circles. Its author is Hannah Cairo, who was just 17 years old at the time. She had disproved the Mizohata Takeuchi conjecture, a formidable conjecture about the behaviour of functions that had stood unsolved for 40 years. Her work has not only toppled the 40-year-old conjecture, but also caused the collapse of a related major conjecture by the legendary mathematician Elias Stein, thereby eliminating what was considered one of the most promising pathways for unifying different parts of the field. Join us on a journey through Hannah's work and get to know the genius behind it. Hannah Cairo's early years were spent far from the world's elite mathematical hubs. Raised and homeschooled in Nassau, the Bahamas, with her two brothers, she describes her early life as marked by a profound sense of intellectual and social isolation. This environment, while confining in some respects, proved to be a fertile ground for a unique intellectual development. She later described her daily life as having an inescapable sameness, a sense that no matter what I did, I was in the same place, doing mostly the same things. This led to a stark awareness of the passage of time, where she would wake up on certain days and realise, I'm just older. It was within this solitude that mathematics became more than a subject, it became a sanctuary. For Cairo, it was an escape, a world that was not confining, a world I could access at any point just by thinking about it. During her somewhat lonely childhood, math was sort of there as a friend to her. She distinguishes between the rote mechanics of school math and the creative act of doing mathematics, likening it to painting. Learning the history and chemical properties of paint is useful, she suggests, but it is not the same as the act of painting itself. For her, mathematics is the painting. Her formal education was largely self-directed and accelerated. Using online resources like Khan Academy, she completed its standard curriculum, including calculus, by the age of 11. From there, she progressed to graduate-level textbooks recommended by a pair of remote tutors, Martin Majid of Wellesley College and Amir Azami from Clark University. Her progress was so rapid and independent that Azami eventually expressed discomfort with being paid. Feeling he was not truly teaching her, as she would primarily read the books and prove the theorems on her own, by the time she was 14, she had taught herself the equivalent of an advanced undergraduate mathematics degree. To grasp the magnitude of Ms. Cairo's achievement, one must first understand the problem she cracked. The Mizohata Takeuchi conjecture was no obscure puzzle, but a central question in harmonic analysis, a field with roots in the physics of waves and quantum mechanics. Harmonic analysis, the field in which the conjecture resides, is the study of how complex functions or signals can be broken down into simpler, wave-like components. We think of it this way. Imagine dropping stones into a still pond. A single stone creates simple circular waves, but dropping multiple stones can create complex interference patterns with high and low points. Harmonic analysis proves that by dropping stones in precisely the right places, one can, in principle, create any shape imaginable on the water's surface. Cairo specialty lies in Fourier restriction theory, which adds a constraint to this scenario. It asks about the kinds of shapes you can build if you are only allowed to drop stones in certain parts of the pond or use only certain types of waves. The Mizohata Takeuchi conjecture made a specific prediction about these restricted creations. It stated that if you are limited to using waves whose frequencies lie on certain types of curved surfaces, the energy of the resulting function, a measure of its magnitude, can only be concentrated in particular well-behaved patterns. Think of it another way. A circle, being curved, cannot have much of its perimeter lie within a single thin, long rectangle. However, a straight line, like the edge of a square, can. The conjecture proposed that the shapes built from these special waves would behave like a straight line, not a circle. They would not be curvy in a way that spread their energy into complex, messy patterns. The Mizohata Takeuchi conjecture was first formulated in the 1980s. It emerged from foundational questions in the study of partial differential equations, PDEs, the formal language used in physics to model phenomena like wave propagation and quantum mechanics. The conjecture is named for two Japanese mathematicians. Shigeru Mizohata was a leading theorist in PDEs at Kyoto University, and Kei Takeuchi published papers in the 1970s and 80s investigating the Schrödinger equation. For 4 decades, the problem remained wide open. Progress was made only on limited, special cases, such as for functions with radial symmetry. The difficulty of the general problem led to a divide in the mathematical community. Some, like the University of Edinburgh's Tony Carberry, who worked on the problem for decades, felt its sheer elegance and simplicity suggested it had to be true. Others suspected that its resistance to all standard methods was a sign that it was ultimately false. The Mizohata Takeuchi conjecture is a key node in a vast interconnected web of problems that define the field of Fourier restriction theory. This field was largely pioneered by a towering figure of 20th century mathematics, Elias Stein, of Princeton University. In the 1960s and the 1970s, Stein posed the foundational restriction problem, which asks the fundamental question: when can the Fourier transform of a function, which exists in a high-dimensional space, be meaningfully defined or restricted to a surface of lower dimension within that space? This question spawned a constellation of related, deep and difficult conjectures, including the Kakeya conjecture, the Bochner-Riges conjecture, and Stein's own conjecture on the behaviour of wave energy. The Mizohata Takeuchi conjecture was seen as a powerful tool that, if proven true, could lead to breakthroughs on these other problems. It was a linchpin, and its removal would have profound consequences for the entire structure. Cairo's journey from isolated autodidact to mathematical revolutionary began in earnest when her world started to widen. In 2021, during the COVID-19 pandemic, travel restrictions stranded her family at her grandparents' house in Chicago. There, she joined the math circles of Chicago, her first significant experience in a collaborative mathematical environment. This led her to apply to the prestigious Berkeley Math Circle, an online summer program known for nurturing exceptional young talent. In her application, at just 14 years old, she listed a range of self-taught subjects that amounted to an advanced undergraduate mathematics curriculum. Recognizing her talent, Zvezdelina Stankova, a Berkeley mathematician and the founder of the Berkeley Math Circle, admitted her to the program. After a second summer with the program, Cairo faced a choice. She had been accepted to UC Davis, but Stankova encouraged her to pursue a more radical path, bypass a traditional high school diploma and undergraduate degree entirely, and instead enroll directly in graduate-level courses at UC Berkeley through its concurrent enrollment program. Her family supported this decision, first moving to Davis, from where she would commute to Berkeley, and later moving to Berkeley itself. This period was transformative for Cairo, not just academically, but socially. She mentioned how she started making friends and feeling good about it, while also acknowledging the adjustment. I didn't have many social experiences, so I still had to learn how to interact with other humans. As the 2024-2025 academic year approached, a graduate course in Fourier restriction theory caught her eye. It was one of the most advanced analysis classes being offered that semester, so she thought she'd just take it. The professor was Ruixiang Zhang, a highly accomplished mathematician whose own path was more traditional, including a gold medal at the International Mathematical Olympiad and a doctorate from Princeton. Zhang was impressed by Cairo's focus and passion and granted her permission to enroll. Within a few weeks, a problem on a homework assignment captivated her. It was a simplified version of the Mizohata Takeuchi conjecture, included by Zhang as a warm-up exercise with an optional extension to consider the full unsolved problem. For Cairo, whose approach to mathematics was one of boundless exploration, the choice to pursue it was simple and immediate. Why should she stop? For 4 decades, mathematicians had grappled with the conjecture, and Cairo, like so many before her, began her pursuit by attempting to prove it. Her weekly pilgrimages to Professor Zhang's office hours became a ritual of intellectual demolition. Each new idea she presented was met with a polite but firm no. These repeated failures, far from being a deterrent, were a crucible. They forced a deeper comprehension of the problem's inherent resistance to conventional approaches, leading her to a crucial and ultimately fruitful act of heresy. She began to question whether the conjecture was true at all. This was the crucial turning point in her journey that ultimately led to her breakthrough. The breakthrough came when she shifted her perspective from proving the conjecture to disproving it. Her insight was to focus on the behaviour of specific types of waves. She realised that the waves in question were concentrated along what she described as thick rectangles. When these rectangle waves were combined, she noticed that the shape of where they meet is not quite at the right angle to agree with the direction that these rectangles are pointing in. This geometric intuition led her to a rather complicated construction using fractals. Fractals are complex, endlessly repeating geometric patterns. They are created by repeating a simple process in an ongoing feedback loop. The patterns are self-similar, meaning they look the same at any scale. Nature is in fact full of fractal shapes. Think of snowflakes or jagged coastlines. She meticulously designed a function built from waves whose frequencies lay on the required curved surface, but instead of their energy being neatly confined along lines, as the conjecture predicted, the waves interfered to create uneven patterns, causing the energy to concentrate in a fractal-like way that the Mizohata Takeuchi conjecture prohibited. She had constructed a mathematical object that, according to 40 years of expert belief, should not exist. Even with the construction in hand, Cairo was wary. "This is something that happens to me often," she later said. She would come to something that looked like a proof and think that she had a proof, but actually would have been wrong. The turning point came in 2 stages. First, she convinced herself, and then Professor Zhang, that her complex construction was indeed correct. Second, in a display of deepening mastery, she found a way to simplify her own work. The first complex proof demonstrated that the conjecture was false. The second, simpler proof, began to explain why. She realized she could achieve the same result by projecting a high-dimensional hypercube down into a lower-dimensional space. This simplification stripped the counterexample down to its essential mechanism, revealing the core reason for the conjecture's failure with a clarity and elegance. The posting of Cairo's paper, a counterexample to the Mizohata Takeuchi conjecture, on February 10, 2025, immediately energized the field. The reaction was one of almost universal surprise and admiration, not only because a major open problem had been settled, but also because of the author's age, the depth and clarity of the work. Seasoned mathematicians who had spent years on the problem were effusive in their praise. Tony Carberry, a senior mathematician from the University of Edinburgh, who called it his favourite problem for nigh on 40 years, was completely blown away and described the elegance of the paper as quite extraordinary. The disproof defied the community's collective intuition about what functions could and could not do. The impact of the disproof extended far beyond the conjecture itself. The Mizohata Takeuchi conjecture is a key node in a network of related problems. Mathematicians had hoped that proving it would provide a powerful method to solve other major conjectures, such as establishing sharp multilinear restriction estimates without error terms. Most significantly, Cairo's work had a direct and fatal consequence for another significant problem, Stein's conjecture. This conjecture was another piece of the grand puzzle concerning how wave energy concentrates. The link between the two was strong, and by demonstrating the failure of Mizohata Takeuchi, Cairo's counterexample also proved that Stein's conjecture is false. In a single stroke, her work eliminated one of the most promising links mathematicians had hoped to establish between different parts of harmonic analysis. The established map of the field was suddenly, irrevocably incorrect. While the disproof closed one avenue of research, it opened another by providing the community with a new tool. Cairo's method for building the counterexample is being seen as a generalizable technique. Julian Vance, a professor who studies harmonic analysis, predicted its future importance, stating, "I am certain that from now on, whenever we come upon a problem of similar flavour, we will try to test it against Cairo-like constructions." Her name became associated with a novel approach to thinking about and constructing counterexamples in harmonic analysis, a lasting contribution to the field's toolkit. The disproof did not create a dead end, but rather a crossroads, forcing the field to reckon with a changed landscape. Researchers who had hoped to use the Mizohata Takeuchi conjecture as a stepping stone must now find new, likely more difficult, paths to prove their results. The disproof has spurred immediate new inquiry. Cairo herself, now working with Zhang as her advisor, is already investigating adjacent problems, including a local Mizohata Takeuchi conjecture. The fall of one major conjecture has cleared the way for a host of new questions and a re-evaluation of the fundamental structure of the field. The multilinear restriction conjecture, which tries to understand how functions behave on curved surfaces, has lost its sharpest tool. A key line of proof is now gone, and this will force mathematicians to find new ways forward. Maximo conjecture, which explores the size of sets containing lines in every direction, is also affected. While not directly disproven, its relationship to the broader restriction program has become more complex. One of the theoretical bridges between these two grand problems has been burned, leaving the landscape of future work more isolated and ambiguous. Cairo does not identify herself as the stereotypical reclusive mathematician. For focused, productive work such as writing, she prefers to be at her desk listening to Bach. For pure, unstructured thinking, she enjoys going for walks. After completing her proof, she applied directly to 10 graduate programs. 6 of the 10 programs rejected her outright because she did not have a college degree. 2 others initially accepted her only to have their decisions overridden by higher-ups in the university administration for the same reason. While the world's top mathematicians were praising the extraordinary elegance of her paper, university officials were unable to look past the lack of a formal diploma. Only 2 institutions, the University of Maryland and Johns Hopkins University, proved willing and able to welcome her based on the merit of her work rather than her formal credentials. In the fall of 2025, Hannah Cairo will begin her graduate studies at the University of Maryland, one of the institutions that recognised her talent over her paperwork. Her journey is just getting started, and we couldn't help but cheer for her. Her achievement stands as a testament to the power of individual curiosity, a powerful challenge to the linear pathways of traditional education, and a stunning example of how a fresh perspective, unburdened by decades of accumulated wisdom, can see what others missed. The world now watches with anticipation, not only to see how others explore the new avenues she has opened, but to see which problem she decides to tackle next.